Um, so thank you everyone for being here. So I am a bit behind on the grading right now, and I do apologize. Just, there's some stuff going on, but I am planning on using this week to just kind of power through some of that grading. So I know there's some homework that's kind of backed up, um, and you have homework that's due tonight, and then also the exam regrades. I haven't checked to see how many people turned in an exam regrade, and that's due tonight as well. So last week's homework, hopefully I'll have graded within the next few days, and then the stuff that's being turned in tonight, hopefully graded by the end of this week as well. The exam too, as I mentioned in an announcement, there was actually a mess up on the calendar. Let's see, what's the easiest way for me to, there's no easy way for me to pull up the calendar. So there is a mix up on the calendar. Exam 2 was scheduled to be for this week, but like I mentioned in the announcement, it's not going to be due until next week. It won't open up until next Monday. So we'll just have a homework due this week. So I'll have that homework posted soon. And the exam review, I'm in the middle of writing, and that will be posted hopefully by the end of today, if not by the end of tomorrow. So the exam 2 review will be posted very, very soon. I think that's administratively all I wanted to say there. Any questions about anything? Any concerns before we get started? All right then. Well, happy Monday. So where we last left off, we were talking about implicit differentiation. So I kind of want to talk about it because we still haven't finished this section yet. And because we're going to be talking about logarithmic differentiation, which requires implicit differentiation, it's in the same section. I want to just quickly review what that process of implicit looked like, since that did happen on Wednesday of last week, a bit ago. So let's just talk about the process of implicit differentiation so we can remember. The whole idea was, hey, we don't have an equation that's y equals. We don't have a y equals equation. We have instead some y's that are being cubed and squared and different things happening to them mixed in with these x's. So we have these y's and x's mixed together, and we don't have an explicit equation. We don't have y explicitly defined in terms of x. And we want to find this derivative. The rule was, you take the derivatives of y as if it were an x, and then the thing that you do is you take care of the chain rule part of it by multiplying by a dy dx if you take a derivative of y. So in this case, when we were doing this derivative, y cubed plus y squared minus x squared equals 5y minus 4, when we took the derivative of 3y cubed, not 3y cubed, of y cubed, that became 3y squared dy dx. So 3y squared is just the regular derivative part, and then adding on a dy dx because we took a derivative of y. So you do that, then your goal is to get all the dy dx terms on one side of the equation so that you can factor the dy dx out, and you're able to solve for dy dx. So that was the process. And we did a lot of examples of it. And now we're going to do potentially the most exciting part of implicit differentiation, logarithmic differentiation. So remember back when when we were doing, oh goodness, how far ago was that? Let's see. Let me go back a tiny bit to when we talked about log rules. Let's see. How far ago did we talk about log rules is the question. Oh, cool. Right back here. So back in section 2.4, we talked about some log rules, and we had some derivatives that involved logarithms. And we said, hey, instead of using like chain rule and quotient rule, we could instead use these log rules to separate the logarithms, to expand the logarithms before taking the derivatives. And by doing that, the derivatives become so much nicer than if we just took it outright. Logarithms allow us these really nice abilities to expand, and that's amazing. And I said, hey, it's really important. I'm sure I put this somewhere. It's really important that you can't use log rules unless there are logs. So we did a bunch of examples that involved logarithms and we expanded them. And we took those derivatives, but then we came over to some other ones where it's like, hey, you actually can't use log rules in a case where there's no logs involved. So we can't take this 7 down in front the way that we can with logs before taking the derivative. Logarithmic differentiation is fun because it allows us to introduce logs in places where there aren't logs. And then we get to use all those log rules. And even though there's no logs in the first place. So here's our motivation. This guy right here. For this guy right here, the cubed root of x squared plus 1 over x squared minus 1. Finding this derivative, if we didn't use log rules, is going to involve quotient rule. It's going to involve chain rule. And why don't we just kind of take it so that we see what it looks like? If I rewrite this, and I'm not going to use anything other than the rules we've already learned: quotient rule, chain rule. I'm taking this derivative. If I rewrite this in its not 1/2, 1/3. And its exponential form, it's x squared plus 1 over x squared minus 1 raised to the 1/3 power. So old way, chain rule plus quotient rule. We take the derivative of the outside. So this whole thing being the outside part, so we take that 1/3, we bring it down. We leave the inside alone. And then 1/3 minus 1 is negative 2/3. Then we multiply by the derivative of the inside. So the inside part, that's going to be a quotient rule one. So we have f and g. For quotient rule, f prime g minus g prime f over g squared. All right, so now we're doing quotient rule. So let's see, f prime, that's going to be 2x. G is x squared minus 1 minus g prime. So derivative of x squared minus 1 is 2x times f, which is x squared plus 1. And then all over g squared. So x squared minus 1 squared. Now, I mean, is it the end of the world in terms of derivatives? No, we've written out some really gross ones. We've written some stuff that's way worse than this. But it is kind of lengthy, right? It's kind of lengthy. So instead, we can be kind of tricky. And the trick is, now that we have implicit differentiation, yeah, there's no logs in here. There's no logs in here, but we could introduce logs in there by taking the natural log of both sides. That's the trick. This is what logarithmic differentiation is. It's introducing logs in places there weren't logs in an effort to make it an easy derivative. So I'm taking this guy right here, and I'm taking the natural log of both sides. So I'm taking the natural log of y and the natural log of the cubed root of x squared plus 1 over x squared minus 1. Taking the natural log of both sides. For this guy right here, we already rewrote it in its exponential form, but let's do it one more time. That's really the same thing as x squared plus 1 over x squared minus 1 raised to the 1/3 power. And making a note here, I have not done any calculus yet. I have not taken any derivatives. All right, this is just algebra I've done at this point. What I am doing is algebra. My log rules say that if there's an exponent, I can bring it down in front, right? And then hopefully you practice expanding your logs like we talked about. If not, remember I did post a video that talked about expanding logarithms to do it quickly and in one step. So this exponent will come in front, and then this is going to turn into subtraction. So if it's division on the inside, it's subtraction on the outside. So you have ln y equals 1/3, and then ln of x squared plus 1 minus ln of x squared minus 1. Again, still haven't done any calculus yet. This is still just algebra. If you'd like, you can distribute that 1/3 in before taking the derivative. That's fine. And now you can take the derivative. And you might think, hey, this doesn't look like implicit differentiation. And it barely is, right? Over here, you have to do a little teeny tiny bit of implicit differentiation. But the other side, you're not going to have to worry about anything special. The other side is just going to be taking the derivative of x like we have the entire time. So now we're going to take the derivative. So with ln y, the derivative of that would be 1 over y. But then remember, you have to multiply by a dy dx because you took a derivative of y. On the other side, with ln's, remember the way that the derivative of ln works? If you're taking the derivative of ln of stuff, it becomes the derivative of the stuff, so the derivative of the inside, over the inside. So for this guy, the derivative of x squared plus 1 is 2x, and then the inside is x squared plus 1, minus 1/3. The derivative of x squared minus 1 is 2x, over the inside, which is x squared minus 1. You've taken the derivative, but now we need to solve for dy dx, and it's one of the easy parts here. So to get dy dx by itself, we multiply both sides by y. Because this y will cancel. We get dy dx is equal to, I'm going to put the y up front for a second. And we're not quite done here. So in the other cases where we did implicit differentiation, we would be done. However, this y is actually not acceptable. This y is not acceptable because this equation, this did not start with, it was not implicit, right? This was an explicit, that was explicitly defined in terms of x. Y is explicitly defined in terms of x. There's no y's on this side of the equation. So it's not appropriate for us to give an answer with y's in it when there weren't any y's inside of our equation up here to begin with. So we just have to do this really small thing and remember that y is already defined here. So we can just replace this y with what y is. Y is the cubed root of x squared plus 1 over x squared minus 1. So we just replace that y. So dy dx is equal to the cubed root of x squared plus 1 over x squared minus 1 times 1/3 times 2x over x squared plus 1 minus 1/3 times 2x over x squared minus 1. And that is our full derivative. You might say to me, Miss Cook, this looks a lot longer than what this took. And maybe in this case, it is a tiny bit longer. First of all, you can get really fast at this part right here. This part right here can happen really fast. I would argue there's a lot more you can forget in here. And I would also argue that if you're looking at something like maybe the next problem or something incredibly complicated, this process becomes really, really nice. This process really eliminates a lot of the tediousness of potentially product and quotient and chain rule happening at the same time. You might think that this answer and this answer don't look like they're the same answer. You're just going to have to trust me here that if you did the algebra, that you would find that this and this are actually the same exact answer. They are the same thing written in different ways. But you'll have to trust me on that one. So that was just one example. Can I take questions on that example before I mention a few things and we do another example? And we will be doing a few examples of this. Give a second for questions. So I'm going to make a few notes before we go on to another example. Just about some common errors, some things to look out for, and some things to know that I'm going to be looking for during your exams that I will mark down for. This first one is really personal to me because when I was a calculus student in college, I did this thing and a tutor told me, you can't do that. And I said, no, I know what I mean. Don't worry about it. I'll show you what I did that I now look back and laugh a bit at myself for. So during this step right here, here's what I would do. I would do, oops, not red there. Let's see, ln. I would do ln y, and then, this whole thing over here would stay x squared plus 1, x squared minus 1. And I would do this. Okay. So my tutor, I did not get through, the tutor did not get through to me on why this wasn't okay. For me, this was like, this is just my notation. I know what I'm doing. Don't worry about it. This is not acceptable. This is not an acceptable notation. So here's the issue. This right here, ln takes an input into it. So in the same way that you wouldn't write pi sine, right? You wouldn't say pi sine. That makes no sense. It's sine of pi, right? There's too many lines in that pi. It's sine of pi. ln is of something. It has to go, the argument has to go after the ln. So writing it like this makes me think that you're looking at it as if it's multiplication, as if you're multiplying by an ln, but that doesn't make sense either. So it's really important that you don't put this ln after it. It has to go before it. I don't care if you come up here and you squeeze it in and you write like ln right here. That's fine. Just don't put it after. Okay, so that's one note. Another note, this step down here where you replace the y is necessary. Make sure you do that. So the original equation, it's going to be right up here. The original function is right up here. It'll be part of your original setup. You just need to make sure to replace it at the very end. The other big thing that I see happening in the many times that I have taught calculus is not taking the ln of both sides here. So what I'll see happening is students will do y equals ln. They'll just put an ln on this side only, but you can't take the ln of one side. You have to take the ln of both sides. Right. So with logarithmic differentiation, those are the things that I see happening most frequently with problems. So just be careful of your notation, even if it's just for you. If it's on an exam, or a homework, it's something I'm grading, so this isn't appropriate notation. Remember to replace your y at the very end, and remember to take the ln of both sides. So what ends up happening if you don't take the ln of both sides? First of all, as soon as you only take the ln of one side, you've completely ruined the equilibrium of the equation. But moreover, at the very end, you won't have this 1 over y, so you won't get this part right here. So your answer will be missing a vital part of it. So just a few things to note. All right, so let's look here. We have g of x equals 3x plus 2 times x minus 1 to the 4th all over e to the x minus 8. We're going to use logarithmic differentiation here. And the trick is that instead of g of x, we're just going to say this guy is y. And it's okay to do that. It's okay for us to call any function y. So this function is now y. And we're going to do logarithmic differentiation. So we're going to take the ln of both sides. So you have ln y is equal to ln of 3x plus 2 times x minus 1 to the 4th. That got really cramped up there. Let me just pull that down a little bit and rewrite it a little bit. 3x plus 2, x minus 1 to the fourth, all over e to the x minus 8. Right? We're not going to do any calculus to begin with. To begin with, we're going to expand this thing. Right? If when we talked about expanding a bit in class, and I told you if you were unfamiliar with expanding to watch my video on expanding logarithms. So if you watched it, just kind of quick recap. The idea is if things are being multiplied in the numerator, then if something is in the numerator, or it's just flat out just being multiplied and there's no denominator involved, it becomes addition on the outside. Any factors in the denominator get a minus sign in front of them. So if you have multiple factors, which are separated by multiplication, you would put a minus sign in front of all of those when you expand it fully. So the way this is going to work when we expand this, it's going to be positive ln of this plus 4, because the exponent will come down, ln of x minus 1, because this guy's in the numerator, and then it will be minus ln of e to the x minus 8 because he's in the denominator. So it'll be a minus in front of him because he's in the denominator. So you have ln of 3x plus 2 plus, bring the exponent down, 4 ln of x minus 1, and then minus ln of e to the x minus 8. Note that you cannot expand these anymore. When you've got to the point where there's just addition or subtraction left on the inside of the ln's, there's no more expanding that can be done. There has to be multiplication or division in order for us to expand those logarithms. But we are at a point where we can take a derivative very nicely now. So we're going to use implicit differentiation, and maybe I'll make a note here. Now take the derivative. Just to make sure you know that we haven't taken a derivative yet. So implicit differentiation, derivative of ln y is 1 over y dy dx. For ln's, it's the derivative of the inside over the inside. So the derivative of 3x plus 2 is 3, and then the inside is 3x plus 2. Plus, there's a 4 here, plus 4 times a derivative of x minus 1 is 1, all over x minus 1, minus the derivative of e to the x minus 8 is e to the x, all over e to the x minus 8. To get rid of the y, we're multiplying both sides by y here. And we already know that y is equal to this bit up here. And it just, my convention is I always put the y stuff in front. So even though the y is over here, I'm going to put the y, I'm going to put this whole thing in front out here. And maybe I'll write it in green so that you know that that's the y part. So we have 3x plus 2, x minus 1 to the fourth, all over e to the x minus 8. And then we have 3 over 3x plus 2, plus, and I'm just going to move the 4 to the numerator because I can. It's the same thing. Minus e to the x over e to the x minus 8. And that is our final answer. I'm just making a note that that whole thing is y. So I'm going to give you some examples to try, but can I answer any questions so far? If you're feeling good with implicit differentiation, then this is going to be a pretty natural extension. So let me give you a few examples, a few ones to try on your own. see. Let's make this one a little easier. Okay, so I'm going to give you, I think, 3 examples to try. Okay, there we go. So I'm going to go ahead and pause for, I'm going to give you 6 minutes, I think. That should at least get you through 2 of them. But I'm going to give you 6 minutes to work through these. Expand them first, then take the derivative. Remember your log rules, and then you got this. All right. So let's go ahead and try these out. Hopefully you've got maybe one of them done. I'm going to go kind of quickly through them. At least I'm going to try to go quickly. Just going to erase this guy, move stuff around so that I have room. All right, so for this first one, I'll do my answers in purple. If we take the natural log of both sides, so we have ln y equals, and then this thing expanded, once you've taken the natural log, 2 ln of 4x plus 5 plus 5 ln x cubed minus 14. And then both of these are in the denominator. They're going to get minus signs. So minus 3 ln x plus 1 minus, now I shouldn't have done this to you to make this actually, you could have easily gone wrong on this guy here. Maybe because I have a feeling people went wrong on it, I'll change it. Technically, if you have ln of 15 x to the 4th, I didn't mean to make this a trick. Technically, you can't bring this 4 in front because this 15 doesn't have the 4th on it. Really, if you had this, this would be split up into ln of 15 plus ln of x to the 4th, and then you could take the 4 down. But why don't I just make it a little nicer, and I'll just move the 4th so it is on the outside of everybody, because I think that's probably how people interpreted it. I'll make this note here just so you know. If you had 15x to the ln of 15x to the 4th, you can't just bring that 4 down in front. But if I change it to be this way, where the 4th is on the outside, then the 15 does have the 4, and you can bring that 4 down in front. So we'll just change it. So minus 4 ln of 15x, which you could separate more if you wanted to, but I feel like it's pretty good at that point. Taking the derivative, we have 1 over y dy dx equals 2 times derivative of 4x plus 5 is 4 over 4x plus 5 plus 5 times the derivative of x cubed minus 14 is 3x squared all over x cubed minus 14 minus 3 times derivative of x plus 1 is 1 all over x plus 1 minus 4 times the derivative of 15x is 15 all over 15x multiplying by y on both sides, remembering y is this guy right up here. You're going to get dy dx is equal to the original y, which is 4x plus 5 squared times x cubed minus 14 to the 5th over x plus 1 cubed times 15x raised to the 4th times, and now here's the thing I like to do, because you can combine these numerators together because they're being multiplied. So I'm just going to multiply those. So we have 8 over 4x plus 5 plus 15x squared over x cubed minus 14 minus 60 over 15x, which also could be simplified because these 15s technically cancel. But because I'm lazy, I'm not going to do any more than that. The reason I like to combine these is because it's less writing, right? It's easier for me to write 8 over 4x plus 5 than it is for me to write 2 times 4 over 4x plus 5. That's the only reason I'm combining them, just because it's easy and it's less writing. So minus this part right here where I really didn't mean to trick you, but probably tricked you there. How was that first one? Did I miss a piece here? Hold on. Am I missing a piece? I feel like I'm missing a piece. 15x. Oh, I am missing a piece. I am missing a piece here. My bad. I'm missing this guy here. Now that I'm looking at it, minus 3 over x plus 1 minus 60 over x over 15x. There we go. Now we have all the pieces. There should be 4 pieces. Oh, excellent, excellent. If you did it in the and you recognize that this was wrong right here, the way that your answer would be different. By the way, just in case anybody did catch this, the way your answer would be different down at this part is you would have, because the derivative of ln 15 would be 0 because the derivative of a number is 0. And then you would have 4 over x instead of, so actually it would come out to be the same. That's funny. I think it would actually come out to be, it would actually come out to be the same derivative. It would actually come out to be the same derivative even if you made a mistake here, because when you make the mistake, the thing that you're making the mistake on is this guy whose derivative ends up being 0. So fun fact, even if you did it wrong, you probably got the right answer. But I'm glad somebody got it right. Hopefully other people got it right, maybe. It's a process, right? But when you get to this point here, it's like, oh my goodness, this derivative is so much easier than what this would be. This would be a mess, guys. This would be a mess to take. Any questions on that before I move to the next one? All right. Then for this guy here, we're going to pretend that this is y so that we can write ln y equals, I'm just going to expand it completely. So 3 ln x plus 1/2 ln of x squared plus 7 minus ln of sine x minus ln of cosine x. So to talk about quickly where all these came from, the x cubed became the 3 ln x. This is being raised to the 1/2 power, so the 1/2 comes down in front and then the inside stays the same. Both of these are factors in the denominator. So these factors in the denominator get split up with subtraction because they're both in the denominator. Taking that derivative, 1 over y dy dx is equal to 3 times 1 over x plus 1/2 times 2x over x squared plus 7 minus the derivative of sine x is cosine x all over sine x minus the derivative of cosine x is negative sine x over cosine x. Multiplying both sides by y, where this guy right up here is y, we get dy dx is equal to that original equation, that original function, and then small simplification I'm going to do here just because I can. These 2's technically cancel, so I'm just going to cancel them. And I'm going to move, like I've done before, I'm going to move that 3 and that 1 together. And then these guys right here make a plus. So I'm just going to do that small simplification. So 3 over x plus x over x squared plus 7 minus, and you could, if you really, really wanted to be fancy here, cosine x over sine x is cotan x. I'm not going to do that, but you could if you really wanted to be fancy here. And sine x over cosine x is tangent x. Sometimes that small simplification is just nice because it's less to write. And it makes it look a little bit cleaner. Can I answer any questions about problem number 2? I'm going to open up a new page to do this next one on just because it's it's getting crowded on this page here. Okay. If at any time you have any questions, please feel free to shoot them out. All right. So looking at this guy, I'm going to rewrite him first. This is a 1/4 power right here. Oh, is it supposed to be like way more zoomed in than that? Oops. There we go. We'll zoom in. This guy right here is a 1/4 power. So it's really like you have x, 3x cubed minus 2x plus 7 raised to the negative 2 all over e to the 6x minus tangent of 6x. This is raised to the 7th, raised to the 1/4. And then this 1/4 gets distributed to everything, and you would just multiply the exponents. So this original really is x to the 1/4 3x cubed minus 2x plus 7, negative 1/2 times 1/4 is negative, sorry, if I said, did I say negative 1/2? I meant negative 2 times 1/4 is negative 1/2. All over e to the 6x minus tangent of 6x raised to the 7 times 1/4 is going to be 7/4. So using this guy right here to expand and calling him y, we have ln of y is equal to 1/4 ln x. And then this would be a plus, but because the exponent is negative, I'm going to write minus 1/2, because plus and negative is the same thing as subtracting. Ln 3x cubed minus 2x plus 7 minus, and I didn't line that up good, there we go, minus 7/4 ln of e to the 6x minus tangent of 6x. Yep, there we go. Taking the derivative, we have 1 over y dy dx is equal to 1/4 times 1 over x minus 1/2 times the derivative of 3x cubed minus 2x plus 7 is 9x squared minus 2 over 3x cubed minus 2x plus 7 minus 7/4, not ln, get rid of the ln, times the derivative of e to the 6x is 6e to the 6x. The derivative of tangent of 6x, the derivative of the inside is 6, so I'll put that outside. And then secant squared 6x. Sorry, my brain just had a moment. All over e to the 6x minus tangent of 6x. Multiplying by y on both sides. You get dy dx is equal to, I'm just going to write this as 1 over 4x minus, I do like to combine these into one fraction. It just looks a little neater. You don't have to, but it looks a little neater. Oh, and then of course, what I forgot to do, which I warned you guys about, see how easy that is to do? I multiplied by y. It happened, but then I forgot to rewrite this guy in here. I'm gonna need more space than that. Beauty of technology. Haha. There it is. So that one's a longer one, required a little bit more, but still better than if you had to do this by hand, by the long way, using our longer methods. Right. Any questions or concerns on this guy here? It does. So somebody in the comments said using the logs makes them a lot easier to solve, and it really, really makes your life easier. Like it is a trick. Like it is not something you might intuitively think of doing, but once you see it and you see it in action, it makes it a lot easier. It makes it a ton easier. Plus, you kind of feel like a wizard because you're kind of like doing wizardy type stuff here. At least that's how I feel. I know my opinion may not be the popular opinion there, but it feels like I'm a wizard. All right. Then let's go on. So here's a fun time that it gets used. It gets used, logarithmic differentiation, that is, when you have an x in the exponent and the base. So the only times that we've seen an x in the exponent is if you had like e to the x or 2 to the x, right? And in both those cases, the base is not x. In other cases, we've seen stuff like 2x squared plus 7 raised to the 9 or something like that. But in that case, the exponent's not an x, right? We've never had a case where both the base and the exponent are an x. And in this case, you cannot use power rule. In fact, you are stuck with either knowing a clever algebra trick or logarithmic differentiation, which kind of basically is the same thing as doing a little clever algebra trick. So what I'm trying to say here is you basically have to use logarithmic differentiation in this case. Right? Taking the ln of both sides allows me to take this x down in front. So I have ln y equals x ln of x squared plus 1. These are being multiplied together. So when we go to take the derivative, this is going to be product rule. F prime g plus g prime f. So the derivative of ln y is 1 over y dy dx equal to f prime is 1, g is ln of x squared plus 1, plus g prime, so the derivative of ln x squared plus 1 is 2x over x squared plus 1, and then f is x. Multiplying both sides by y, we have that y right up there. So the y part is x squared plus 1 raised to the x. These guys multiplied together, 1 times anything is just what's, the anything part. So this is just ln of x squared plus 1 plus 2x times x is 2x squared. Is that simplification necessary? No, but I mean, it's kind of nice. It's kind of nice. And there you go. There's your answer. So in the case where you have an x in the base, and in the exponent, you have to use logarithmic differentiation. You cannot use power rule. That is not a thing. All right. Let's do another one where that's the case. So in this case right here, we have ln x raised to the sine x squared. We're just going to call this guy y again. We're going to take the natural log on both sides. Ln y equals ln of, all right, ln of this whole thing. Ln of ln x raised to the sine of x squared. This sine x squared is the exponent, which will come down in front. So we have sine of x squared multiplied by ln of ln x. Right, a little complicated here. This is going to be product rule again. I'm going to be a little careful here just because we have some chain rule going on, and I am going to write this whole thing out. So we have f and we have g. So my f is sine x squared. My f prime, the derivative of the outside, is cosine x squared times the derivative of the inside is 2x. To write that a little nicer, we could bring the 2x out front. 2x cosine of x squared. For g, it's ln of x. G prime, right? This is, for logarithms, remember, it's the derivative of the inside. So the derivative of the inside, the derivative of ln x is 1 over x, all over the inside, which is ln x. Derivative of the inside over the inside. To simplify that, 1 over x over ln x is the same thing as 1 over x ln x. So taking the derivative, 1 over y dy dx is equal to f prime g plus g prime f. So f prime, 2x cosine of x squared, that's f prime. G is ln of ln x plus g prime is 1 over x ln x, and f is sine of x squared. Multiplying by y on both sides, and this whole thing right here is y. We get dy dx equals, we'll put y out front, so ln x raised to the sine of x squared times, we'll just leave some of these parentheses in here, 2x cosine of x squared ln of ln x, 2, 3, yep, plus, the only thing I could do to really simplify this part here, I could just put this in the numerator just because they're being multiplied and it just makes it a little bit easier to read. Don't have to, but once again, small simplifications like that are kind of nice. And there, bam, we got an answer. A little bit complicated because you got that ln of ln x, which is just a little bit more than we're used to, but it's not awful. All right, any questions on that one? On any of these exponents with x and bases with x? Okay. The last thing to talk about in this section is implicit differentiation and horizontal/vertical tangent lines. All right. So let's do a problem. Find all points where the, oops, that's not my pointer. Find all points where the curve represented by the equation 9x squared plus y squared minus 18x plus 6y plus 9 equals 0 has vertical and horizontal tangent lines. So to start this, tangent lines in general, you're going to need to find that derivative first, right? So to find slopes of tangent lines, you need a derivative. So before we do anything, we're just going to find the derivative of this guy. So the derivative of 9x squared plus y squared minus 18x plus 6y plus 9. So for the first part, 9x squared, that's going to be 18x. The derivative of y squared will be 2y, and then because it's a y, we put on a dy dx for chain rule. Derivative of 18x is 18. Derivative of 6y is 6, but then we have a dy dx. And the derivative of 9 is 0. And the derivative of 0 is 0. So we don't really need to even have this 0 here, right? Anything with a dy dx on it, which are these two, are going to stay on this side, on the left side, and then I'm going to move the other guys over to the right if it doesn't have a dy dx in it. So we have 2y dy dx plus 6 dy dx equals 18 minus 18x. I put the 18 first so that because it's positive, and then minus 18x. But you could do negative 18x plus 18. That would be the same thing. Factoring out the dy dx, 2y plus 6 equals 18 minus 18x. And then as a reminder, we're dividing by this leftover stuff right here on both sides. So we get dy dx equals 18 minus 18x over 2y plus 6. Now the question is asking where the points are where this curve has vertical and horizontal tangent lines. So here's the important thing. For a horizontal tangent line, so for a horizontal slope, it's a line like this. This is horizontal. The slope is 0. For a vertical line, the slope is undefined. Right? So kind of thinking about what that means. For the slope, so for the horizontal part, for the slope to be 0, you need to have the numerator be 0. Right? The only way a fraction can be 0 is if the numerator and the numerator alone is 0. So it can't be 0 over 0, but when you have 0 in the numerator. So it's a horizontal tangent line when the numerator equals 0. So I'm going to take the numerator, this guy here, and set it equal to 0. Right, so you get 18 equals 18x. Divide both sides by 18, and you get x equal to 1. To find the y value, because we want points, right? They said points. To find the y value of those points, you're just going to plug this x value into your original equation, just like we've done before. So, looking at this, we have 9 times 1 squared plus y squared minus 18 times 1 plus 6y plus 9 equals 0. So 9 plus y squared minus 18 plus 6y plus 9 equals 0. 9 plus 9 is 18, minus 18 is 0, so this simplifies to y squared plus 6y equals 0. To solve that, you are factoring, so y times y plus 6 equals 0. You get y equals 0 and y equals negative 6. That means that there's 2 different points where this happens. You have 2 different y values, so there are 2 different points where that happens. So you have horizontal tangent lines at, both of them have the same x value. They have x equal 1. So at 1 comma 0 and 1 comma negative 6. Those are the 2 different y values. And now, because I ran out of space, let's actually just shrink that up a little bit. I'll try to take up a little less space here. For this undefined part, so for the vertical line, because it asks for the vertical tangent lines as well. For the vertical tangent lines, you're looking for where the slope is undefined. The slope is going to be undefined if the denominator equals 0. So there's vertical tangent lines when the denominator equals 0. In this case, 2y plus 6 is our denominator. And it's the denominator of the derivative, right? Because the derivative gives us slope of tangent line. So we have 2y plus 6 equals 0. 2y equals negative 6. Y equals negative 3. In this case, we are finding x values by plugging this y value into the original equation, which all the way up here. But you have your notes in front of you, hopefully, so you can just kind of reference that. So to find the x value, I'm plugging this in. I'm plugging negative 3 in for y. So we have 9x squared plus negative 3 squared minus 18x plus 6 times negative 3 plus 9 equal to 0. 9x squared plus 9 minus 18x minus 18 plus 9 equal to 0. 9 plus 9 minus 18 is 0, so those cancel. So we have 9x squared minus 18x equals 0. Factor out a 9x. X minus 2, 9x times x minus 2 is 0. So x equal to 0 and x equal to 2. And the y value for both of those is negative 3. So we have vertical tangent lines at 0, negative 3 and 2, negative 3. So you can find, so I guess the thing to say about this one, with vertical and horizontal tangent lines, if you're doing implicit differentiation, if you're trying to find where the tangent lines are horizontal, you're just letting that numerator equal 0, and then finding the x or y values that you can get. You'd only be asked this on questions where it'll be easy to obtain those answers. So you would find the x values or y values and plug them back into the original equation to find the corresponding x or y value of the coordinate points. But the horizontal tangent lines are going to be when the numerator is 0, and the vertical tangent lines are when the denominator is 0 of the derivative. So I think that should be it on this section. Yeah, that's it on this section. Can I answer any questions on the 2.5 section before we move into 2.6? I'm going to be shortening 2.6 a tiny bit. It's a short section to begin with, but I'm going to be shortening it a tiny bit. Okay. Well, then let's move into 2.6. All right. So here's the thing. We're a little bit behind. We were supposed to be talking about related rates today, which we're not going to get to talk about until Wednesday. So I'm just going to be cutting some material. I'm cutting this stuff. If you want to talk about this with me later during my office hours, over email, I'm happy to talk about what this stuff goes over, but I'm not going to go over that stuff. I am not going to go over the inverse function theorem. But what I do want to talk about from this section are the derivatives of inverse trigonometric functions. Okay. Those are the things I want to talk about. Here are new derivatives for you. Bam, new derivatives. So you have some new derivatives. These are of the inverse trig functions. Remembering the way that the inverse trig functions work. So if you have sine of theta equals y, the inverse is sine inverse of y is equal to theta. So essentially, sine shoots out a number. So trig in general just shoots out a number. Inverse sine or inverse trig outputs an angle. In terms of taking derivatives, that information's basically not even necessary. But what is necessary is knowing that this little negative 1 up here is not a power, right? This is this negative 1 here. What I want to remind you of from your trigonometry is that this negative 1 is not a power. It refers to the inverse, right? It is not a power. It is an inverse, and they have their own derivatives. Here they are, right? because your tests are open notes, you don't need to worry about memorizing them. So just here they are. Ta-da! So let's use them a few times just to get used to these new derivatives that we now have. So let's find some derivatives. Let's look at sine inverse of t squared. From the previous page, the derivative of sine inverse of x was 1 over the square root of 1 minus x squared. Right here, we don't have an x on the inside, we have a t squared, so we are going to have to use chain rule. Right? So we have an outside function, outside function, and we have an inside function. With sine inverse, we are using chain rule here. If you're taking the derivative of sine inverse of, I don't care what you're taking, what's inside there, right? The inside stuff. This is going to be equal to 1 over 1 minus all that stuff squared times the derivative of that stuff. In our case, that stuff is a t squared. So I'm going to change this to a t for a second. T squared, t squared, t squared. Right? I'm just taking this thing right here and putting a box in it. So this part right here is literally this with just the x replaced with a box, and then just remembering chain rule, so we're multiplying by the derivative of the inside there. So f prime of t is equal to 1 over, I'm going to do this in green. This is the derivative of the outside, 1 over the square root of 1 minus t squared squared. So that's the derivative of the outside. Times the derivative of the inside. So the derivative of t squared, which is 2t. Just kind of cleaning that up a tiny bit. You can move that 2t on top. And this could be 1 minus t to the fourth if you wanted to clean it up a tiny bit. Bam. So the key thing here is you're not treating this as if it were sine of t squared raised to the negative 1. You are not doing that. Right? It's not raised to the negative 1 power. This is important to recall from your trig lessons. It's not raised to the negative 1 power. It is inverse. Some trig teachers, maybe this is important to point out, some trig teachers don't use this notation. In particular, if you're coming from high school pre-calculus, this might be true. They might use arc sine instead. So these two are the same thing. So if you're more familiar with arc sine, it's the same thing as sine inverse x. A lot of people would argue that this notation makes a lot more sense because we put powers here. Like if sine squared x is equal to sine x squared, why would this not be true, right? Good question. Because it's not. Because it's not. But these are the same. Arc sine and sine inverse x are the same thing. So just as a note. There's a fly flying around. Okay. Oh well. All right, here we go. So, as a note, for this next derivative, we're going to need tan inverse. So I'll just write what tan inverse's derivative is. It's 1 over 1 plus x squared. So if we have something else on the inside there, the derivative will be 1 plus whatever that stuff is squared times the derivative of the stuff. Right here, x is being multiplied by tan inverse, so we are going to have to do product rule there. Let's do pink. So on this first part, we're going to have to do product rule. F is x, f prime is 1. G is tan inverse of 2x, right? So tan inverse of 2x. So just kind of filling in 2x there. G prime is going to be equal to 1 over 1 plus 2x squared. So here's the important part. When you're plugging in that 2x there, you're squaring the whole thing, not just the x. So it's the entire 2x gets squared. Times the derivative of 2x, which is 2. And I'm going to just simplify it a little bit just because it will look nicer in our final answer. So this is 2 over 1 plus 4x squared. So what I did from here to here, 1 times 2 is 2, and then 2x squared is 4x squared. So for our derivative, remember with product rule, f prime g plus g prime f. So f prime is 1, g is tan inverse of 2x, plus g prime, which is 2 over 1 plus 4x squared, times f, which is x. That's not our full derivative, though, so that's the derivative of this part. And then for the final part, we have an inside and an outside. So minus derivative of the outside, so the derivative of tangent x, or tangent whatever, remember, is going to be derivative of tangent is secant squared, so the secant squared of whatever times the derivative of that inside part. In our case, this little box is 1 plus 4x squared. I know it got very cramped in there. So 1/4 secant squared of 1 plus 4x squared is the derivative of the outside times the derivative of the inside. So the derivative of 1 plus 4x squared is going to be 8x. And there it is. If you're feeling fancy and you want to simplify a little bit, here's what a little bit of simplification will get you. You can combine these. So first of all, 1 times anything is just itself. 2 times x is 2x over 1 plus 4x squared. And then this 1/4 and this 8x, when they multiply, just give you 2x because 8 divided by 4 is 2. So you could do minus 2x secant squared of 1 plus 4x squared, if you wanted to do just a tiny bit of simplification there. Once again, not necessary. I'm more interested in you getting this part than I am of this, but it's nice to practice those algebra skills and make things look a little neater. Can I answer any questions on those examples? So why don't I give you guys 2 to try out real quick. Let me just make something up real quick. Let's do e to the 4x times cosine inverse of x cubed plus 9, and g of x is equal to, let's do tan inverse of, let's make it a little fancy, sine squared x. Right. I'm going to put on a 4-minute timer. All right, I'll pause the recording. All right. So hopefully at least one of these you're able to finish. So I'll start with this part A. F of x equals e to the 4x times cosine inverse of x cubed plus 9. So this is going to be product rule, but we also are going to have to do some chain rule in here. So we have cosine inverse, and his derivative, if you look back on the other page, -1 over square root of 1 minus, it would be x squared, but I'm just going to put a blank there since we're dealing with chain rule, derivative of the outside, and then it's the derivative of whatever that inside part is. In our case, this will be x cubed plus 9. I know it's really tiny, but it's x cubed plus 9. So we're doing product rule. We have f and g. F is e to the 4x. F prime is 4e to the 4x. G is cosine inverse of x cubed plus 9. G prime, so the derivative of the outside, -1 over the square root of 1 minus, make sure you put parentheses here, x cubed plus 9 squared, times the derivative of x cubed plus 9. So the derivative of x cubed plus 9 is 3x squared. Which, if we wanted to clean it up a little bit, the numerators can be multiplied together. So you'd get -3x squared over the square root of 1 minus x cubed plus 9 squared. So our derivative f prime of x, and again, abusive notation here because f, this f here and this f here, it's abusive notation. But this f and g belong to just the product rule part of it. F of x is really this entire equation. So f prime of x is equal to, with product rule, f prime g plus g prime f. So f prime is 4e to the 4x. G is cosine inverse of x cubed plus 9, plus g prime, -3x squared, over 1 minus x cubed plus 9 squared. And then f is e to the 4x. How did that first one go? How did that one go for everybody? Pretty good. Okay, I'll take a pretty good. Went well. I'll take that as well. I'll take that. Good. Those are all good things. Any questions or concerns about that first one? Okay. This next one, we're going to have to be a little bit careful. As a reminder, for tan inverse, if you have tan inverse of stuff, this derivative is going to be 1 over 1 plus all that stuff squared times the derivative of the inside stuff. The weird part here is that this inside stuff is sine squared x, right? Sine squared x is fine. We'll just leave it like that for there. But this is the same thing as sine of x squared, which is important because when you go to take the derivative, this derivative, this is going to require chain rule. Where you take the derivative of the outside, so that's 2 sine x, that's just power rule here. Take the 2 down, sine x, reduce 2 by 1, so it becomes 1. So 2 sine x, and then the derivative of sine x is cosine x. Right? Really important there that you're doing chain rule on that guy. So g prime of x, looking at this whole big thing, right? 1 plus sine squared squared. You can make that sine to the 4th if you'd like, but for ease of reading your notes later, I will leave it as sine squared x, so you don't get too confused. All right, squared times then the derivative of sine squared. Did I write a 4 there or a 2? This is supposed to be a 2. It kind of looks like a 4 because the blue bled into it. But that's okay. Times the derivative of sine x squared, sine of x, quantity squared, is 2 sine x cosine x, which we got from right here. The simplified version of this would be 2 sine x cosine x over 1 plus sine to the 4th x. But I didn't want to write that right here just because I wanted to be very clear. These are both A-OK answers. Any questions on that one? So really, the important thing, this is nothing new. This is just, I'm giving you a new rule, but I'm not really giving you anything super, super new. This is all the techniques you've used before. It's just you're getting a new rule added in. It all works the same way, though. It works the same way as everything you've been doing this entire time with regards to chain rule. I think we have time for you to try out one more. We have like 3 minutes left. So real quickly, I want you to try this one on your own. I will remind you, because it's on the other page, that the derivative of secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. All right, so I want you to do this derivative. You are going to have to do quotient rule. I would not suggest doing logarithmic here. Just take this flat out. Just do quotient rule here. And I would suggest, with the other ones, how I did this box thing. You might find that useful. Oh no, this one doesn't have chain rule. Just kidding. So you won't need to. I thought it had a chain rule in it. There's a chain rule here, but not here. So do this derivative real quick. Quotient rule. I'm going to put a 2-minute timer on. All right. So really quickly on this guy, we're going to be doing quotient rule. So that's f prime g minus g prime f all over g squared, where this guy right here is f, this guy right here is g. So if f is secant inverse of x, f prime is this whole thing right here. So it's 1 over the absolute value of x times x squared, the square root of x squared minus 1. G is e raised to the x cubed plus 1. His derivative will be the derivative of the exponent, so 3x squared, e to the x cubed plus 1. So dy dx will be equal to f prime g, so e to the x cubed plus 1, minus g prime, 3x squared, e to the x cubed plus 1, f, which is secant inverse of x, all over g squared. So e raised to the x cubed plus 1 quantity squared. So hopefully that one wasn't super bad. Just your quotient rule that we've been doing this entire time. And I know we are 2 minutes over. If you need to get going, that is totally fine. There's just a few things I'm going to add on to the end here. If you need to look at the recorded video later, you can always do that. But this is the answer to this guy. Hopefully that went well. I do want to talk about the answers to the remainder of this section. I think there's only 2 problems left in this section. Yeah. And if you want to do these on your own, I just wanted to talk about the answers to this one. So for this one, you're finding a tangent line. I'm just going to tell you that the slope should come out, if you do this one, to be 3 pi minus 6. So the line ends up being y minus 3 pi equals 3 pi minus 6 times x minus 1. And for this one down here, the derivative ends up being, again, this is just so you can do this ones on your own. dy dx equals 8 times the square root of 1 minus x squared y squared over 3x times 1 plus 16x squared minus y over x. Right. So if you want to give those ones a try, that is there for you. Can I answer any questions about either of these 2 sections? I will set up a time for us to do an exam 2 review, because on Wednesday we're certainly not going to have time to do an exam 2 review, since I have we have to do related rates during that class time. So we'll set something up. I'll look at my schedule. It's a little busy this week. We'll figure something out though, and we will do an exam review sometime before the weekend or maybe during the weekend if we have to. And then exam 2 will open up on Monday. Yeah, maybe Friday. Like Friday would be my goal. I do have meetings for, I have one-on-one meetings that I have to do with my other classes. So I just need to block out time for it. So I'm going to think on it. If you have personal suggestions on times and you want to send me an email about, hey, it would be really great if you could do it at this time, feel free to send me those emails. I'd be happy to take those into consideration when I schedule a time. And I will post a review just like I did last time. So the entire review will be recorded and posted. So if you can't come during that time, no problem. It'll be posted. If you can't stay for the whole thing, no problem. It'll be posted. So it'll be there regardless. If you want to see it happen live, you'll be able to see it happen live. Otherwise, it'll be there. All right, guys. Well, thank you guys for being here. Happy Monday. We are at the beginning of week 8, which means at the end of this week, guys, at the end of this week, we are officially halfway done. So you've made it. You are halfway through Calc 1 almost. I hope you guys have a fantastic Monday, and I'll see you guys Wednesday. And if you have questions, stay around. You can stick around to message them to me, or you can send me an email. All right, bye, everybody.